In this video, we're going to continue discussing modeling with quadratic functions. We've been doing this since we began discussing quadratic functions, and today we're just going to get into a little bit more detail. Since we started talking about quadratic functions, we've been talking a lot about like projectile motion. So maybe something's being dropped, or maybe something's flying through the air. There are other examples of modeling with quadratic functions, and you're going to continue to see these through different or various word problems. Some examples might be, in addition to projectile motion, engineering and physics, like building bridges, economics, finance, right? When do we make the most profit, or when do we have the least loss? Biology, optimization, so again, optimizing things, and how can we get the most area out of something? Computer graphics, we've talked a lot about it in sports, environmental science, and medicine. This is just to name a few, and this can be found on my website under 5.1. So I gave you a definition here about mathematical modeling, and it says a mathematical model is a mathematical structure, equation, graph, diagram, table, all the things that we've been using to kind of describe data that fits the trajectory of a quadratic function. And so it can be used to describe and study a real situation. It helps simulate, understand, and predict behaviors or outcomes within various fields by translating complex situations into mathematical formulas or structures. On this page, I've just summarized the different forms of quadratic functions. So you have standard form, vertex form, intercept form. They can all be graphed in similar yet different ways. They all have an axis of symmetry. That's what AOS stands for, and I put a little note down here. Each one of them, you can find your vertex. It lies along that axis of symmetry. Sometimes for standard form, you can factor it. Other times you're going to have to use quadratic formula to find those x-intercepts, or you can use a table of data to find inputs and corresponding outputs. Vertex form is pretty straightforward. You've been given the vertex, and you can again use a input-output table to find other points. And intercept form is pretty nice because you've actually been given the x-intercepts, at which point the axis of symmetry is in the middle of those x-intercepts. All right, so we're going to use that stuff that we have learned in the past to help us write some quadratic functions. Now, some of these will be applicable, and some of these are going to be abstract. For example, example 1, you're just given this graph on the right-hand side, and we have to write a quadratic function in vertex form for this parabola that's been shown to us. So the vertex form of a quadratic function is going to look like this. If we are given the vertex, then we know what h is. H is -1, and we know that k is 4. We are also given some other point here, which we can then use as an x and a y value. So we'll use x is -2, and we'll use y is +2. Okay, so if I know all of those things, I can plug them all in, and I can find a. So I'll start with plugging in 2 for y. I don't know a yet. I'm going to figure that out. Plugging in -2 for x. Subtracting, and now h is a -1. I'll plug that in. Square all of that, plus k, which is 4. I'm going to simplify what's in the parentheses first. So this is actually a -2 plus 1, or a -1 squared. Now I'll do exponents. So -1 squared is just a +1, so I could just write a. And now I can solve for a by using the subtraction property. Now this makes sense that a would be negative because my parabola is in fact opening down. I'm going to go ahead and plug a in, and I'm also going to plug in my vertex h and k. I'm not going to plug any values in for x and y because there are infinite points on this function, and each one of those points is represented by a different x and y. So we can write it like this, or in function form you do f of x. Plug, instead of a, I'm going to plug in -2, x minus, and I'll go ahead and write -1 for now. I'll come back and simplify it, plus 4. Now, this is really x plus 1, which is why my parabola was actually moved to the left one. And plus 4, plus it means it was moved up 4. Moving on to example 2, we're going to write a quadratic function in intercept form. This one is more of a real-world application. It's not so abstract. Many highway engineers or road engineers would be working with this type of problem. So the surfaces of some roads are shaped like parabolas to allow rain to run off to either side. And recall, this is also true of football fields. We did a similar problem with football fields. We're going to write a quadratic model for the surface of the road shown. So let's see what kind of information has been given to us in this problem. I have this road that is parabolic shape, and it's barely noticeable, right? So one end of the road is at this point, which I will call 0, 0. Notice that is an x-intercept. Another point of the road is over here, and it's 24 feet away from that first point. And that is another x-intercept at 24, 0. We're also given one more point. We're given where the road is curved up about 0.2 feet above that horizontal surface. And that happens about 17 feet from the beginning of the road. So we'll call that just some random point, some x and some y. Or we're going to use that to help us figure out some of our unknowns. So they said to use intercept form, which makes total sense because I'm given 2 x-intercepts and 1 additional point. So remember, intercept form looks like this, where your x-intercepts are your p and your q. So I'll have y, or you could use f of x if you want to put this in function notation, a times x minus p and x minus q. All right, so my p and my q here are my x-intercepts. So we could say that p would equal 0 and q could equal 24. Now, how would you know this if you didn't remember that? So let's use this x-intercept of 24. So for example, if I know that one of my x-intercepts is 24, when we see these in factored form, we usually set them equal to 0 to use the zero product property and solve for each x-intercept. So the question might be, how do I get this equation x equals 24 instead equal to 0? I could subtract 24 from both sides, and that would give me x minus 24 equals 0. So there it is as a factor, which then I solve and go right back up to x equals 24. Or you can just remember that in intercept form, your x-intercepts get plugged in for p and q. All right, so plugging in my 2 x-intercepts gives me something that looks like this. I'll simplify because what's x minus 0? Well, that's really just x. So I'm going to go ahead and write it as y equals a times x times the quantity x minus 24. Now you can take that additional point, that x and that y value, right? So we were given an x of 17 and a y of 0.2, and that's going to help me figure out what my a is. So I'm going to plug in 0.2 for y. I don't know a. I do know that x is 17. I'll plug that in. Again, in this factor of x minus 24, I'll plug in 17. Now it's all about simplifying. So simplifying and solving for a. Now 17 times negative 7 is negative 119. So I'll go ahead and I'll write that times a. Solving for a, we're going to divide both sides by negative 119. And a actually becomes a very small number, which I think makes total sense because we are talking about a highway. It's barely, or a road, where it's barely noticeable that it's even parabolic in shape. Okay, now just taking my a, I'm plugging it back in, and I think I will plug it into this version because I don't need to have a factor that says x minus 0. So I will rewrite this as a, or y equals, and then negative 0.00168x times x minus 24. You can also distribute and end up with an x squared, or you can leave it in intercept form. Example 3 is abstract. They've just given us 3 points. Each one of these points has an x and a y value. They want us to write a quadratic function using these 3 given points. And these could be 3 points of any data out there in the world. We don't know. But we're going to go ahead and we're going to write ourselves a quadratic function in standard form that passes through these 3 points. Now, standard form looks like this: ax squared plus bx plus c. So I'm going to use all 3 of these points, and I'm going to plug them in for x and y 3 different times, because notice I have 3 different variables or three different unknowns that I must solve for. And in order to do that, I'm going to have to set up a system of equations. I will need 3 equations and 3 variables in order to solve this. All right, first equation. My y for my first point is -1, so I will write -1 equals, and then I have a, and then my x value is -2. I will square that, plus I don't know what b is, but I do know x is -2, and I am unsure about c. That's going to be my first equation. Second equation, I'll use the second point. So my y value is 11. I don't know a. Plugging in x, that's 1. Squaring that, plus b. Plugging in x is 1, plus c. And my third equation, I will use the third point. My y is 27. A, I'm not sure of. X for this one will be 2 squared plus b times 2 plus c. I'm going to now take each one of these equations and I'm going to simplify them. I'll go over here to the right. So my first equation becomes -1 equals, now -2 squared, well, that's 4, so that's a 4a minus 2b plus c. Next equation, simplifying, I've got 11 equals, well, 1 squared is just 1, so I'll just write a, and 1 times b is b, so I'll just do plus b plus c. That's a nice easy one. Okay, and then my third equation, I've got 27 equals, well, 2 squared is 4, so I've got 4a plus 2b plus c. All right, so 3 equations. First equation, second equation, third equation. Now this should ring a bell. We did this before, and now we're just going to apply it. We're going to take 2 equations at a time, get rid of a variable, do it again to the other 2 equations, and then combine those 2 equations that just have 2 variables so that we can start solving for a, b, and c. Now I notice my constants don't have any coefficients at all. So it might be a wise idea to try and get rid of those c's first. So maybe I'll take the first equation and the second equation, and I will get rid of c. So how about the first equation? I'll multiply by -1. So if I multiply that first equation by -1, I'm going to end up with a +1 equals -4a positive 2b minus c. Okay, and then I'm going to take the second equation, and I'm just going to leave it exactly as it is. So +11 equals a plus b plus c. So now I can get rid of the c's. Combining, I end up with 12 equals -3a plus 3b. So there's a new equation. Now I'm going to do the exact same thing. So I think between equations 2 and 3, I can also get rid of the c. So how about I'll start with equation 3, which is 27 equals 4a plus 2b plus c. And then I'll multiply the second equation by a -1, getting -11 equals -a, -b, -c. Combining those, the c's go away. And I'm left with, let's see, 16 equals 3a plus b. Okay, so now I notice between these two equations, wow, I think my A's are opposite. My A terms are opposite of each other. So I think I can just combine these two equations and hopefully get a value for B. So let's see, I'm just going to take that second equation there. That's 16 equals 3A plus B. Looks like I get 28. The A terms go away. I'm just left with 4B. Divide both sides by 4. I get the fact that B equals 7. Now I can take that value of B and plug it back into, how about this 16? This one here. Okay, so I get 16 equals 3A plus 7. So solving for A, I'll subtract 7. I get 9 equals 3A. Dividing both sides by 3. A is going to equal 3. And now lastly, I can take my A and my B and plug it back into any of my first three original equations. How about I'll do the second equation, since they don't have any coefficients. It's just A, B, and C all have a coefficient of 1. So we'll say now 11 equals 3 plus 7 plus C. So 11 equals 10 plus C, or subtracting 10 from both sides, C will equal 1. So now I have all of my coefficients, and I am ready to write my equation in standard form. So we'll go y equals, or you can write it in function form, f of x, or h of x, or g of x. Y equals, and my a was 3, so 3x squared, plus, now my 7, or b is 7, so 7x, and c is 1. And there it is in standard form.